was, I should say, a huge success in India. He's a welding engineer and acting quality manager at Special Metals Welding Product. He has worked for multiple suppliers of welding consumables in many areas from research, technology to application and quality roles. In addition to his experience as a product development engineer, he is a certified welding inspector and has NQA1 lead auditor qualification. Now we have Mr. Lew Shoemaker. Is a metallurgical engineer employed by Special Metals since 1974 and working in product development, technical services and marketing. He is now a part-time in SMC's Research and Technology Group. His areas of interest include alloy application, welding, fabrication, and corrosion. So I am sure we all are going to have a very interesting session today. So I first invite the Special Metal management team to take us through a brief introduction on special metals, followed by the lecture. Thank you all.
Thank you. Can you enable the share screen?
Yeah.
Thank you.
Can you try to share screen now?
No, it's saying it's still disabled, host disabled currently right now.
Hold on a second. I'll make you the host so you will be able to present it, right?
Maybe.
There you go.
John, this is Lou. Can you hear me okay?
Yes.
Okay.
John, now you're the host and you should be able to share the screen. Could you try that?
There we go. Yes.
Thank
you.
you.
Okay. Can everybody see that screen?
Yep.
Yes, sir.
Yeah, we can see it. No problem.
Okay, very good. Thank you for the introduction. I'll keep it pretty brief, but obviously met all of the hosts and staff. For us at Special Metals, it's an honor and privilege for us to be able to finally put this together. I was overseas actually with Garotra over there at the Weld show earlier this year, and then again before that, prior at the end of 2019. And that was one of the first times, at least a little while in a few years, that we've been able to have someone from the Special Metals welding side come over to India. Basically see the growth of the that have been going over the last 5 years. Can we just make sure everybody ensure that you're on mute? Presentation. Just a few administrative items here.
Mr. Girotra,
just make sure you're on mute.
Mute yourself.
Mr. Girotra, could you please mute?
Okay, thank you. So just a few admin items, just ensure you're on mute. For the audience that's out there, you have the chat that is off to the right side of your screen. So if you have questions as we go through the presentations, go ahead and put those questions up off to the right-hand side. We'll go back through those after we have concluded each of the presentations, and we'll go back through more of the Q&A session. What you see in front of you is the schedule of the different events that we're going to be going through, starting off with Sam on the different but not difficult presentations, and we'll work our way through the schedule. Once we've completed all the presentations, we will then open it up to a Q&A session, and essentially we'll just try and work back from the beginning as those questions came up. We understand that's probably going to be a lot of the larger part of the actual timeline for the duration of this teleconference. But if there's something that's extremely important, please just put it off to the side and make some notes of it. If we really need to address it in the presentations, we will, but the intent is to hold all questions until the end. With that as well, we do have a short introductory video we would like to show everyone, so I'll play that here in a minute before we start the first presentation. It just gives the overall view of our plant in the United States and outlines our production facility. Special Metals has been around for over 100 years. In the welding side and on the manufacturing side of the high temperature nickel alloys, we are a leader and innovator, and we continue to innovate over the years and into this new 21st century that we're pushing through. It's something that we take great pride on, but also not just our quality and brand of our material, but the technical expertise that we have and we instill and we put in every day. And I think you'll be able to get a lot out of that through both the presentations and the Q&A session from our technical team, Sam, Brian, and Lew. And so we hope this is a very beneficial opportunity for everyone, and hopefully we can do this more going forward. So without further ado, I'm going to go ahead and play a quick intro video here.
You are playing the video?
John,
Is everybody seeing the video?
Yeah,
No.
you started.
Are you able to see it?
No.
Not yet.
No.
John, you might want to stop the share and reshare the screen with the video link. So if you're playing the video, you want to
Gotcha.
stop share and reshare because we're just seeing the presentation.
Okay.
Stop share and then reshare the video app.
Got it. Here we go. Okay, is that better?
Just about to start. Yeah, it's better. Now we can
Yep.
see the.
Okay, okay. All right, thank you.
Thanks. John, there is no sound in the video. In case there is, you might want to just tune up your output, audio output.
Okay.
Stop share, tick mark, and then restart. Bottom left.
You said you were not getting the audio with that, correct?
Yeah, there was.
Bottom left. No.
Okay, 1 second. I see it. I see it. Okay. Sorry about that. We'll try a third time. My apologies.
No worries.
Good?
Yep.
Yeah, now it's okay.
Okay, thank you very much. So again, with that being entailed on there, we'll go ahead and kick into the first presentation, which will be with Sam Kiser with Different But Not Difficult. So let me just bring that for you, Sam, here. Okay, can you see that?
Yep.
Yes.
You might just want to make the full screen. Yeah, there you go.
Okay, there you go, Sam. Over to you.
All set. Thank you, John. And thank you, gentlemen from Weldwell and from India. It's indeed an extreme pleasure for me to be able to visit with you again, half of the world away, and again after over 20 years. I was there some time ago with and toured your country and had a delightful experience visiting with you and customers and so forth. And since then, I've been enjoying communicating with various ones of you in solving problems and in developing welding procedures and talking over problems that you've had. So it's not that we've been apart, it's just that we haven't seen each other. So it's a pleasure to be able to see everybody again. So thank you for this opportunity. The presentation, Different But Not Difficult, is over 70 years old, although it has been altered and added to and so forth as the inheritors come down the road and they see other things that need to be added. So it's a collection of welding engineers and welders from the just before the 50s in adding things to help people learn to weld nickel alloys. So the presentation, though, does not lose its effectiveness in communicating the differences between steel and nickel alloys. We have added a couple of features that tell you why those differences exist and how you should not fight against them. Basically, I have grandchildren, and sometimes they listen, and sometimes they listen but don't hear. I think I just lost my screen.
Sorry, sit down for a second. It should back up.
Yep. Well, anyway, where I was the effectiveness of this. And the whole idea is, and I was saying about my grandchildren, they listen, but sometimes they don't hear. And so a lot of times, unfortunately, some welders are that way as well. And we all need to listen carefully and then attempt to implement what is spoken. So these differences are basic differences. It's very difficult to try to make the nickel alloys behave like steel and so forth. So we'll just talk about those differences and see if we can't come to a conclusion of how to change our procedures and our techniques to manage the differences. So John, if we could have the first slide. These are the four differences, and nickel alloys require much greater cleanliness than steel. It has a less fluid or more viscous weld metal than steel welding products. You also get less penetration into the weld joint. Now that's when we're talking about welding on nickel alloy base plate. And then there are convex bead shape requirements to help prevent centerline cracking. And also, we might add to this list, or we might say it at the same time, we need to backfill all craters. When we come to a stop, we need to stop and fill in with a little bit of extra metal to make sure that the crater is convex. So those are the differences. Next slide, John. So the first basic difference is cleanliness. And this comes into a really kind of a neat thing. We're going to talk later about the low penetration into nickel alloy base metals. And one of the reasons for that is the surface or the nickel alloys need to be kept away from sulfur of all types. And so that part plays into the penetration talk that we'll be getting into later. But basically, we have to watch out for heavy surface oxides on plate. Nowadays, I don't think we get too many plates shipped from suppliers with a heavy hot rolled surface oxide. But if you do, that's one of the things we need to watch out for. It needs to be removed before you start welding. And the other one, we need to keep embrittling elements away, especially those that contain sulfur, phosphorus, and so forth. Next slide, John. So why do we need to get rid of oxides? Well, the nickel alloy oxides melt at much higher temperatures than the nickel base metal. If you notice the temperatures on the left there, nickel melts at somewhere around 2635 or so, and nickel oxide melts at 3794. I guess in your economy it's 1446 C and 2090 C. So there's a huge difference between the melting temperatures of the oxide and the base metal. If you compare that with steel or the iron oxides, iron melts 2798 thereabouts, and iron oxide FeO is about 2588. and iron Fe2O3 hematite is about 2850 or so. So the iron oxides and the iron base metal melt at about the same temperature. And what that means is that now you can't talk most welders into doing this, but it's possible to weld right through iron oxide, even hot rolled oxide, because the oxides melt at about the same temperature as the base metal. So if there is an oxide present, you basically can burn right through it, or even float it out, or even reduce it. So that's the first basic difference in cleanliness. We've got to remove the oxides. Next slide, John. And if you try to weld through the oxides in nickel alloys, typically you can get inclusions like you see in the screen here. And you can imagine what that would look like if you tried to cut a transverse side bend through that and bend it. It'd pop open. And if you didn't find those in your quality assessment of the plate, it might cause a problem in service. So we got to get rid of the oxide inclusions. Next slide, John. So we can remove the oxides by grinding, abrasive blasting, and pickling. And we've got a wire brush. We've got to do not use wire brush. That's not exactly right. Wire brushing will not remove the heavy, tenacious oxides that attach themselves to nickel alloys, like in high temperature service or in hot rolling. Wire brushing between passes with all processes is a good thing to do to keep it clean. But if you have a heavy, tightly adherent oxide, wire brushing won't remove it. What it does is it shines it up and makes it look like it's clean, but it's still there. And the best way to tell this for the welder is to look for a topographical difference. The oxide always floats on top of the puddle, and if it solidifies and attaches itself, there'll be a difference in the topography. There'll be a slight upstep when you get to the oxide. John? Second one is embrittling elements, and these are the most commonly encountered: is sulfur, lead, and phosphorus. But there's plenty of others, and tin, zinc, bismuth, antimony, and arsenic. The "and" doesn't mean that arsenic is the last one. There's plenty of others. So just need to watch out for foreign materials that might be on your plate before you start to weld. John? And these are various sources that you can find contaminating elements. Probably ones that we've seen, temperature indicating sticks, marking crayons. I've had a visit with a guy up in the lumber territory, and he was using a great big yellow crayon that it said right on the thing it had lead oxide in it. So it's a potential problem. But and another one, a fellow was setting tubes in a tube-to-tube sheet arrangement, and he was kind of bumping them into place with a lead hammer. And so there's just all sorts of sources of contamination. Go ahead, John. And this example, this is probably the worst we've ever seen, so we wanted to put it up. But this is a nickel 200 tube, and it's used, typically nickel is used a lot in the caustic industry. But you can see that there was sulfur on the surface of this material, and it was TIG welded, sort of, but you can see the kind of cracking that you get. So sulfur forms a eutectic with nickel and forms low melting areas, and it just kind of falls apart while you're welding. Next slide. And let me go ahead and just leave that slide there, but just to say, several of these materials, the contaminants, like sulfur and phosphorus particularly, they do form eutectics, which are lower melting point combinations than the base metal. So they're the last to solidify, and they can cause you big problems. The others are low melting point metals, And we didn't have on our list mercury, but it is possible to have mercury contamination, and it's a liquid at room temperature. And so you can imagine what mercury would do to your material. So anyway, just keep it clean. Get it clean and keep it clean. So let's see. I think we're ready for the next slide. The second basic difference is the less fluid or more viscous nickel alloy weld puddle. And so we have to change gears again. We have to consider that the nickel molten metal is more viscous than steel. In fact, quite a bit more viscous. One of the comparisons that we used to make is that nickel weld metal is more like, well, I guess you know what molasses is, but like cold molasses or cold syrup versus, that's what nickel alloy molten metal is, versus water, the steel. So the water flows easily and quickly, and the molten nickel metal is more viscous. Next slide. So the first thing the welder will do, if he's not experienced with this, he'll say, well, it's obvious that I'm welding it too cold. I need more amperage. And so you turn it up and it's still cold. And you turn it up some more and it's still cold. And pretty soon, if you see in the little caricature, the welder has his electrode glowing red. And that's generally what happens. So we have to not try to make the nickel alloy weld like steel. We have to change our mind and change our technique so that we don't get too high of an amperage and have weld defects. And certainly porosity. If you've ever had Swiss cheese, we used to illustrate that by a slice of Swiss cheese with porosity in it. Next slide, please. So what we have to do, instead of turning the amps up, is we have to use a weave. It should not exceed 3 times the core wire diameter. So if you're running an 1/8 inch rod, then you don't want to weave more than 3/8 of an inch. And the main thing, is very important to hesitate at the end of each weave to fill in the undercut. And we'll show you a picture in just a minute. Go ahead, John. This is a drawing of a cross-section of a weld. And if you can imagine you're the welder and you're welding from one side to the other, and the other, and the other, you should not use a whip weave. That's common among steel and steel welders. What you have to do is, if you can imagine what it's like when the electrode goes to one side and it burns into the sidewall, it leaves a little undercut there. And if you move the electrode away quickly or too soon away from that, the weld metal doesn't have a chance to catch up and fill in. But what happens is the slag is designed with a low viscosity, and so the slag will fill up that undercut. And maybe some of you have experienced that in the live welding forums that we've had. We'd always ask if how many have, hold your hand up if you have had wagon tracks before. And it's amazing, probably 30 or 40% of the audience would admit to having wagon tracks in their first welds. John, if we can have the next slide. It's a picture of what is causing wagon tracks in your x-ray. The wagon tracks are those intermittent straight lines along each side of the weld, somewhere down in the weld. And if you notice at the end section there, there's the place where the slag trap is being caused. And so that's what happens if you weave too fast. So you need a slight pause, weld here and hold, weld here and hold, weld here and hold, and so forth, because of the puddle viscosity. Okay, John? So the third basic difference is less penetration. And now what we're talking about is when we're welding on nickel alloy base metals. So there is considerably less penetration in nickel alloys than in steel. So this is a cross section. The top row of pictures up there are actual cross sections of materials that these welds were made autogenously on steel on the far left, stainless steel in the middle, and Inconel 600 on the far right. And if you notice, these were all made at the same amperage, voltage, and travel speed and so forth, same size plates and so forth. But because of the nature of the materials, the penetration is quite different, as you can see. And so if you look at the mild steel, the penetration is probably more than double the penetration in the nickel alloys. So you have to remember that when you're attempting to make repairs, or if you've got a tight rolled over bead in the edge of a base metal, you can't burn that out like you do with steel. You got to take a grinder and open it up. I remember when I was first learning to weld in the weld lab, the guys had a plate set up for me. They threw the weld rods down on the table and laid a grinder there and said, if you don't make any mistakes, you won't need this grinder. And you can imagine how many mistakes I made. But one of them was from trying to burn out. If you have a tight groove that you've created by a rolled over bead, you cannot burn that out like you do with steel. So you have to grind it, open it up. And we'll talk about that in difference in joint designs. But one of the things that's kind of different about this is what causes the difference in penetration. And it's good to know. It's called Marangoni convection. And basically what causes fluid flow in the puddle itself is either the surface active elements or lack of surface active elements. And if you notice, we said before, nickel alloys, low sulfur is terribly important. If you look at the specifications for nickel alloys versus steel, steel is typically O2, O3 sulfur. Nickel alloys are double O2, double O3 sulfur. Sulfur is a surface active element. And when you add sulfur, or if you have sulfur, like in a steel alloy, it acts as a surface active element, and it increases the surface tension of the pool. And so what happens then is it causes the flow direction to be on the right with the high sulfur, so that the superheated material directly under the tungsten is directed down, and the fluid flow comes in from the outside and then goes down. So that creates deeper penetration. In the case of the low surface active element of sulfur in the nickel alloys, the fluid flow is reversed. It flows from the middle of the surface outward. And so then the superheated metal directly under the arc flows to the outside, and it creates a wider, more shallow pool. So it's good to remember this, and we do have two references for you. The guys that wrote about this back in the 80s were Heipel, and Roper. And if you look for the Welding Research Supplement of August 1981, pages 143S through 145S, or the reference 2 is, again, Welding Research Supplement of April 1982, pages 97S to 102S. And we can supply that information later if you didn't jot it down. But those are two excellent papers on the Marangoni convection. Next slide, John. So the whole idea is this is a basic difference between nickel and steel. Don't try to change it, accept the lower penetration, and we have to make allowances for it. And one of them is, the next slide, John, is, well, let's see, I guess we'll get to the groove dimensions and groove geometries later. But the fourth basic difference is the convex bead shape requirements. With a concave bead shape, you're extremely subject to centerline cracking. And the same is true with craters. You might make a beautiful convex weld, and then if you stop and just break the arc abruptly, you have a crater and you get cracking. So you need to make all parts of your bead slightly convex. And if you have a bead like the one on the left, you need to slow down. Next, John. The reason for this is that if you have a concave weld, you've got the surface tension, surface in tension, and so the last to solidify, the center line, is the one that's most easily pulled apart. If you have a convex surface, then it's not in tension, at least it doesn't have the full dose of tension, and so it's much more resistant to centerline cracking. Okay, John? Next. And these are just actual cracks that, that occur in a fully restrained joint. And typically this is what happens. You can expect this with nickel alloys. Next slide. Other parts of nickel alloy welding is not any more difficult than steel and actually is simpler. Most nickel alloys, at least the solid solution nickel alloys, are single phase from melting all the way down to sub-zero temperatures. So interpass temperature is not critical usually. Now with the stainlesses and those that tend to form carbides and so forth, then it's much more different. And steels, you know, that form multiple phases like martensite and cementite and so forth are much more critical than nickel alloys. Generally, with the solid solution nickel alloys, you don't need any preheat. And secondly, you don't need post-weld stress relieving. Now, there are some applications where you might get into stress relaxation cracking, and you will need a post-weld stress relief for those. But typically, you don't really need post-weld stress relieving. And finally, the cooling rate is not critical. So we keep a bucket of water if we're welding on something that is not critical. We just dunk it in the water to keep it cool so we can keep welding. So next slide. And this is what I was referring to before. The joint designs for steel must be, for nickel alloys, must be different from steel. You notice that we've opened the included angle up from 60 for steel up to 80 for nickel alloys. And that gives you room to be able to weave the electrode appropriately. And then if you look at the U-groove in the bottom part, we've opened up the groove, and you notice the land for nickel alloys is not as thick as it is for steel because of the penetration differences. Next slide. So what do we need to remember when we're welding nickel alloys? We got to keep the weld zone clean. When we made the alloys, we made it with low sulfur. Please don't introduce any more sulfur. Next. And we have to manipulate the weld metal with a weave technique, and that weave technique has to include a brief hesitation at each side to let the puddle catch up with the arc. And we got to accept the inherently lower weld penetration that you get with nickel alloy base metals, and we have to open up the joint, and we have to make thinner lands. And the next one is we've got to maintain convex beads, and we have to remember to backfill our craters so that we have convex stops. But if we remember all these things, then we hopefully will become a successful nickel alloy welder. And if we don't, then all we have to do is refer to these ideas again and see what's going wrong. But again, it's been a pleasure talking with you folks, and thank you for the opportunity, and look forward to hearing from you in the question and answer session. Thank you.
Okay, thank you very much, Sam. Appreciate it. That was a good presentation here. We'll get on to the next one here. So next, we're going to have the joining nickel alloys, and our presenter is going to be Brian Gaal, our welding engineer on site here in Newton. Let me get your presentation up here, Brian. Okay, Brian, over to you.
All right. Well, thank you very much, John. As everybody mentioned, I did visit and tour your country back a couple years ago in February. It was a very nice tour. Got to meet a lot of neat people, see a lot of different things, and very much enjoyed everything. What we're going to talk about now is going to be kind of a little bit of an abridged version of joining nickel alloys. I'm going to kind of go over some of the avoid the fundamentals of welding, but the something I do want to keep in mind is keep in mind all the basic fundamentals that Sam just mentioned, and then we'll go into a few more detailed tricks and trades that I've kind of seen as I've been out visiting with customers with some of the bigger problems that tend to come up. So first, we just want to remind everybody that there are multiple processes you can use with nickel alloys. You're not limited to just TIG welding, gas tungsten arc welding, MIG welding, gas metal. Shielded metal is still very popular, very useful due to its portability, especially for small repairs and things. As well as submerged arc, if you are doing some bigger welding or some cladding situations, that can be a very useful process as well. Next slide. As Sam mentioned, nickel cleanliness is very important. Basically, we just want to remind you guys, degrease, remove all those oxides before you put a wire brush or a grinder on there. If you don't do that, you're going to potentially contaminate the grinder, and then you're basically, as you remove the oxides, you're going to be depositing some of the other surface contaminants that may be on there. And then we'll talk about shielded metal. These are kind of just some high level, high advantages and some limitations. The big thing to remember is, if you're doing a small little repair, shielded metal may be a very practical way. You don't have to pull out a lot of different cables. You don't have to worry about shielding gas. You can do this outside. It's not the highest deposition rate, but it's still a very good way to do a small repair with minimal setup. Next slide, John. One of the things I've come across multiple times, particularly as I traveled around the world, is something to be aware of is just the different types of power sources and how they can affect a stick electrode. What you're seeing is kind of some oscilloscope plots of what the actual power, energy, and current is coming out of a welding machine. So the original design way back, a lot of people were using motor generator welders, and as you can see, that was a very straight line power, and that affected the electrode kind of in one way. Then we got to the transformer rectifiers, a little bit newer technology, still very flat line power, maybe a little bit of ripple, but for the most part, you had a very consistent DC type of power. And at the bottom, we get to the new generation of inverters, and that's where we did start seeing a lot of different things going on with the electrodes. Particularly when they were first introduced, there were some pretty big problems with some of the very highly alloyed electrodes because the power just wasn't affecting the electrode the same as it had in the past. And as people started getting some experience and some hard lessons learned, they have actually adjusted the inverters to be more friendly to nickel alloys because of the higher resistivity in the core wire. And to the point now, you're actually you can get a much smoother, more controllable arc with an inverter than you could in the past. But again, that's something to just be aware of, that difference in power source can cause a little bit of adjustment in parameters. The newer inverters, again, they do weld a little bit smoother, a lot better with the nickel alloys than in the past. And that will affect the performance of a stick electrode, and not negatively, but just something to be aware of, that there is a difference. Next slide. As Sam mentioned, the start and arc break and restrike is very critical with stick electrodes, mainly because the nature of creating a concave crater is very susceptible to cracking. What we have is kind of an illustration of a good proper arc break and restrike technique for a stick electrode. The picture on the right we actually have is a modified version of that is commonly used on test plates and weld labs, where you're going to be machining or grinding off those start stops. What that actually does is a little bit different weave pattern where you're actually bringing that start up upon the previous bead. And that makes it very easy to grind off and then very easy to remove any potential porosity or any issues with that start. Not always the prettiest pattern, so if you're not going to be machining the weld or it's going to be left, you may want to take the risk and have that start going forward where you're actually welding over it. But if you are doing a lab plate or a qualification, it is, you know, very good idea to pull that out where you can eliminate any chance of problems of start porosity. You can pull that out and you can grind it off and remove it. Using that technique definitely helps passing x-rays and making your qualifications go a little bit more smoother. All right, now we'll kind of skip over to some gas metal arc welding or MIG welding. This is probably gaining a lot of steam in the last few years with the nickel alloys because you can do much more continuous welding. We're now starting to put wire in drums, so you can do, you know, not thousands of pounds, but at least, you know, 200 to 500 pounds without having to change a spool of continuous welding. Obviously gives you faster travel speeds, much higher deposition rates, so you can put more metal down. Even with the proper equipment, you can still go all position. We're talking something like a pulsing type power source. You can run the solid wire vertical up or overhead. You do, with those advantages, you've got a little bit more limitations, much more complicated welding equipment, a lot more things to check before you get started to make sure everything's set the way you think it is. The big productivity gains are not always recognized on thinner materials, at least with manual welding. Another advantage of gas metal is it does automate much easier than a stick weld or a shielded metal arc welding. So that's where we're starting to see things like robotic welding come into place and be used even in the automotive industry with some nickel alloys, where things like automotive exhaust systems where they're trying to extend the warranty, and one of the weak areas in there was the weld. So they're now going to a much higher nickel alloy for that weld, which makes it a much more robust process and basically gives you a lot longer life on some of these parts. A safety feature just to mention, there is a lot more energy coming off of that arc. So you do want to make sure you're protected a little bit better as far as, you know, making sure your hood's covering everything. I'm sure everyone's once or twice has gotten that real bad sunburn on their neck where the welding hood didn't quite cover everything. So you want to be very aware that there's a lot more energy out there. So you do want to protect yourself as best as possible. Next slide. Okay, so one of the #1 complaints I've always come across when it comes to gas metal arc welding is wire feeding problems. I can't mention how many times I've gone out to places and it's, you know, we're having issues with this wire feed. And the biggest reason for the trouble is nickel alloys have a wide range of stiffness, and that's due to their cold working rates. The nickel alloys can go anywhere from very minimal cold working to something that cold works incredibly quick. So as we process these, that can lead to a wide variety of stiffness levels, if you will, in the finished wires. So for example, things like a nickel 1, which is commonly used for butter, may be very soft. You may have to adjust your settings. You really want to shorten that torch lead all the way up to 625. That can be, you know, very stiff, and you can get away with much longer weld leads and can do a little bit more things with that. But again, you do have to make sure you've got the wire feed with enough torque on that motor to push those longer lengths. One of the big tricks I've seen used commonly with robotic welding primarily is adjusting your roller types. Historically, solid wire was always fed with a V-groove smooth roll wire feeder roll. One of the neat little tricks, and you can kind of see it in the picture down here, I've seen people alternate a grooved wheel or a knurled roll, which is typically used for a cord wire product, with the V-groove, and that really bites into the wire a little bit and gives you a lot more control when you're feeding that. That's very helpful if you're using an advanced MIG process or you know, a robot type welding where you're going to have a lot of quick movement. You may, you know, end up with some situations where that torch gets in a little bit of a twist, but it really helps avoid that. And then the other just kind of common sense, you know, we've got the photo of the foot, you know, somebody stepping on the lead and, you know, causing a kink. You really want to watch that and try to avoid that. I've even been into places where they did need to run a longer lead because of just the nature of the part they were making, but they created a little bit of a support for that weld lead, so it stayed, you know, straighter and wasn't kind of bunching up or causing unnecessary kinks, which make it much more difficult to feed that wire. The other second, probably largest problem I hear about is people complaining about burn backs on the tips. And what that really comes back to a lot of times is this type of shielding gas that's used for the nickel welds. Normally, we recommend as this kind of a safe catch-all is 100% argon. There's argon and helium gas blends that work very nice for different reasons. But the thing to remember when using these gas blends is your heat capacity for that gas goes down. And a lot of these torches are rated based on CO2 shielding gas. So if you notice on the graph, the CO2 can absorb a lot larger amounts of heat than, say, typical argon or even argon helium blends. So if you've got a torch that may be rated for 300 amps with CO2, you know, you really may only be able to use that torch continuously around the 150 to 170 amp range for a nickel alloy if you're running that argon shielding gas. The other thing, we recommend on these is the water-cooled torches. Again, with the higher resistivity of nickel, you build up a lot more heat, and when you're continuously welding, those contact tips just don't get the cooling they normally would get with the CO2 shielding gas. So if possible, and there is continuous welding at higher amperages, a water-cooled torch can really save you a lot of headaches and burn backs and stops as you're trying to weld. Next slide. Some of the common defects that are a little more unique to gas metal and with nickel alloys, as Sam mentioned, one of the big problems is lack of fusion. It's very easy to kind of make a MIG weld that looks real pretty that you're just kind of laying on the surface, but those surface oxides and all the other nuances of nickel welding really play against that when you get into gas metal arc welding. So you do need to be very cautious, just like with a stick weld where you're making sure you burn into that sidewall and let it fill in. You want to do the same thing with the MIG weld. Make sure you're burning in that sidewall. But the other challenge, if you go too slow with the MIG weld, one of the very common defects that comes up is something called overlap, or typically referred to as rollover. If you look at the weld picture on the right, basically what happened is they were going just a little bit too slow, and that very sluggish metal kind of just rolled over, and it just sat on top of the base metal and didn't really burn in. It gives you, potentially lack of fusion. And then as you come in with your next pass with the lower penetration of a nickel weld, you just don't burn into that previous bead and don't really penetrate in and get rid of those problems. Just for anyone doing robotic welding, sorry, John, the rollover can be a very big problem in tight corners with robots. With steel wires, it's pretty common to be able to kind of almost do a 90-degree turn with those robots without breaking arc because of the fluidity of the steel. When you get into the nickel alloys, they're just not that fluid. You have to be a little more careful, and sometimes if you're in a very sharp corner, you may want to break the arc, pause for just a second just to avoid that buildup as that robot arm turns and doesn't really move the puddle. It just kind of rotates to get around that corner. Next slide. So gas tungsten arc welding is probably one of the most preferred welding processes from a mechanical standpoint with nickel alloys. Does have the advantages of very pretty, very high quality welds, very minimal spatter. You've got one of the few advantages where you can do an autogenous weld, which is no filler metal, or you can add filler metals in multiple ways, whether it's manually dipping the filler metal into the puddle, or we can set up a wire feeder to feed wire in at a very controlled rate, which does help increase the productivity and the deposition a little bit, but there's some nuances to work with that. The other thing is the limitations. You do need to be very protective of that shielding. Things like drafts, open windows, all that stuff can kind of cause you some problems to temporarily lose shielding, and then you run into some problems where you could have maybe some porosity. Even if you don't get to the point of full porosity, you can get some oxygen induced in there and end up with some nickel oxide that's pretty tenacious. People that have done a lot of mechanized gas tungsten are probably familiar with the term floaters. If you lose temporary shielding, you can create some of those floaters that can be very problematic because, as Sam mentioned, they're very high temperature melting oxides that are not going to be vaporized, if you will, by the tungsten torch. They're just going to kind of be pushed around, and eventually they're going to go to the sidewall and become an inclusion. That's just a side note on this. One of the big problems with the floaters or the inclusions, the better you are at doing mechanized TIG welding, the bigger problem they can be. Because as you get very precise in control of that with the mechanized process in TIG, the floaters tend to go to the same spot and they tend to deposit on the same side of the weld bead. And then when you come back and do either an ultrasonic inspection or sometimes an X-ray, you can run into what's called a linear defect, which can automatically disqualify a lot of pieces because you've done such a great job controlling that weld metal that those little oxide floaters always went to the same side. And then when they do the UT, it's a linear indication, which can be an automatic reject. Next slide. So we mentioned the gas protection. One of the things we really want to we recommend is the shielding gas lens, and then also using the largest gas cup that's practical. I always say practical because it would be great if you could use, you know, a 6-inch diameter gas cup to just flood that and keep that weld protected. However, that you just may not be able to reach into a groove. A lot of times you'll see people adjusting their tungsten well beyond the gas cup, and that causes a lot of problems because the further you stick that tungsten out, the less shielding you're going to actually get to protect the tungsten and that weld. If possible on a mechanized process, shielding trailing gases are always recommended because that just gives you a little extra shielding to let that weld cool a little more and reduce the amount of oxides that could be on there. Next slide. Okay, so submerged arc welding is probably one of the least utilized, in my opinion, for nickel welding. It can be very high deposition rates. You've got very good weld protection because, you know, the arc's submerged and encapsulated in the flux. Does require a little bit more equipment, not always practical in all positions. It does work out of position. It's just not very practical to figure out a trough to support that flux if you want to weld overhead. But again, can be used with many nickel alloys. The one caution I will point out is, and this goes for shielded metal arc welding as well, any nickel alloy that's relying on a precipitation strengthening mechanism, such as a gamma prime or gamma double prime, you may run into some problems trying to use any kind of flux-based weld process because the aluminum and the titanium, which are really forming those strengtheners, tend to end up, they've got a very high affinity for oxygen, and they tend to end up in the slag as opposed to staying in the weld metal. So you can lose a lot of those goodies, if you will, the aluminum and the titanium that provide the strengthening from the gamma double prime. The other thing to just be aware of, on that same note, you do tend to burn out some of the niobium and the chrome when you're doing submerged arc welding. So you need to be cautious that you're getting all the strengthening elements in a solid solution alloy that you think you're getting as well. Next slide. One of the biggest problems that I see seem to be coming up when it comes to nickel welding is the flux burden, or the level and the height of the flux that's kind of used. With steel, it doesn't seem to really bother it if you kind of just completely bury the arc. If you ever see flash, you'll see guys have scoops, just, you know, throwing more flux onto the weld to just cover everything, and it doesn't really seem to cause any problems. But with nickel fluxes, you typically have some outgassing, so you have to kind of balance that that height. You know, if the burden is too high, you can trap some gases. There's some there's some weight of that flux that can actually depress the nickel metal, and you get some very interesting phenomena where the metal will actually be oozing out the sides of the weld, and you've got flux kind of coming out the side, and it just kind of makes a very big mess where you don't typically see that with a steel submerged arc flux. You know, if that burden is too low, you do tend to get a little bit of arc flash. You know, too much of that can be detrimental to the operators, but There are a couple scenarios with some particular nickel alloys that solidify very quickly that most of the guys that run that in submerged arc do actually want to see just the hint of a little bit of arc flash coming through, because they want to just barely cover that weld puddle, so they don't trap any gas. They give it as much time as the gases to outgas on that weld, so they don't solidify and trap and get porosity. This is a very exaggerated picture of a flux burden, but that does kind of clearly illustrate the difference. If you were using a typical flux chute, you know, and just dumping it on there, you're going to end up with 3 to 4 inches of flux burden that can really cause some problems in nickel, where on a steel weld, not really as much of an issue. Next slide. One of the last things that is commonly overlooked is the sample preparation of a nickel alloy. What we have in this picture are 2 identical 625 alloy welds. These would be the face bends that are typically required for qualification of filler metal. The one on the left was prepared at a brand new state-of-the-art lab that had really nice CNC machining abilities, but they had very little, if any, experience with nickel alloys. If you're not real familiar with machining, it's not uncommon with steels to remove as much as an 1/8 to 1/4 of an inch on a single pass with the CNC machine to get these samples ready. However, with a nickel alloy, you're going to be down limited to about 5 to 10 thousandths thickness per pass. If you don't do that, you tend to run the risk of work hardening the surface of that nickel alloy. And what you get is a bend that looks something on the right where it's completely cracked. And they're very thin surface type defects, but they're very quick to, you know, fail a bend test. I mean, as you can see, that had pretty good sample prep. You know, they did a nice radius on those corners to avoid problems there, but the whole surface was just cut with a CNC fly cutter, very high speeds, and just work hard in that surface just enough that when it bent, it just cracked it. The one on the right was the same identical welding conditions. The only difference was the way the sample was prepared. It was machined and lightly ground, and then bent in a wraparound jig, which really didn't have a lot to do with it. But if you have an option, that does tend to work a little better with the nickel alloys. All right, so now we're going to talk about a little bit of nuances for cladding nickel alloys. Again, do remember all your basic fundamentals. That's the biggest thing I can always point out to everybody is, more often than not, something is overlooked with shielding gas that causes some problems versus, you know, a big, you know, we didn't have a groove prepared correctly, or, you know, we used the wrong wire. It's not as common to come across those, but somebody forgetting that, you know, they got a hole in their gas line or something is a much more common problem. And then as we talk about the difference in what we're doing when we're cladding a piece of equipment or a piece of a component versus trying to join a piece of a component. Well, the reason we're cladding this is primarily for corrosion resistance. We're not really adding some strength to it. We want to use a less expensive steel to make the structural component, and then we want to clad a layer of nickel alloys to protect that steel from the rest of the environment. So we're worried more about corrosion resistance and matching, whereas when we're joining, we're really worried about matching the strength. So that component, you know, that weld has just as much strength as the rest of the component. When we're cladding, we typically try to go after low penetration. You know, we really don't want a lot of mixing of these two metals. We want to minimize that. Again, where we're joining, we really want to burn in there, so we make sure we get a good, you know, uniform weld metal. On the cladding side, it's not uncommon to see direct current, electronegative or reverse polarity, or an AC to minimize the heat that's going into that base metal. You can still clad in direct polarity or DC electrode positive, you know, direct polarity. It's just there are some advantages to using the reverse polarity or an AC to minimize that amount of penetration. The other difference is, you know, joining, you may have a slight weave to a little bit of a stringer bead. When you're cladding, you know, it's very common to do some oscillation, so you're really spreading that weld out to kind of get more bang for your buck, spreading that weld thin with a mechanical method versus just relying on the weld to wet out itself. Next slide. The other thing, as we mentioned, the oscillation, just be aware of the different types of oscillation equipment and make sure you're matching the oscillation equipment to your welding process. Things like a pendulum oscillator actually rotate kind of something like this. Works very well for gas metal arc welding because of the forgiving nature as that stick out arc gets a little bit longer. However, if you're doing something like a TIG process, as you pivot like that, you actually create a longer arc and you're changing your parameters a little bit as you do that versus something that would be a straight line that would be, you know, back and forth with the same arc length the whole time. The other thing is to keep in mind some of the variables that you can typically always adjust in an oscillation. You can adjust the ends of that weld, whether you're trying to minimize one side versus the other to put a little bit more metal where you don't have a bead versus the side that you're tying into it. And again, there's no right or wrong process. It's just be aware of the differences and the nuances and make sure you're applying the best type of oscillation for what you're trying to do. Next slide. Some tricks to minimize dilution. Weld bead step over when you're doing cladding is probably the biggest and best trick. If you can imagine, the closer you put the weld beads together, the more you're actually burning into the previous weld bead and not the base metal. So you can minimize the dilution and you can also you know, burn less of the base metal in there. What we've got on the left side are a very wide step over, something in the neighborhood of a 50% or less bead overlap on the top, and then the bottom is probably closer to about a 60 to 75% bead overlap. And as you can see, that bottom fusion line becomes straighter, which gives you less potential problems. You're actually burning less of the base metal, so you've got less dilution. You're not pulling up as much of that iron, which can cause some problems and reduce your corrosion rates. One of the other tricks you can commonly do with some type of cladding processes is playing with your torch angle. You know, a completely vertical torch will be kind of a good blend between good penetration and good reinforcement. Now, if we want to angle our torch down to have a good leading torch angle, we're actually not burning into as much of the base metal. We're spreading the bead out a little bit, and we're going to minimize the problems with dilution. So both of those tricks, as well as, you know, welding uphill or downhill, can be very useful to minimize that dilution, so you're maximizing the corrosion resistance of the alloy you're putting down. Next slide. All right, so now we're going to kind of skip over to some of the more common applications for cladding and some of the more common alloys that are used for cladding. What you see here is a picture of a ID weld clad with Inconel 625. That's one of the probably workhorse nickel alloys. It's incredibly useful for a lot of things. Very good corrosion, very good strength. You know, kind of when in doubt, it's a really good go-to nickel alloy. It's great for overalloying dissimilar welds. You know, if you've got a stainless where the weld's being attacked, it's a very good way to just upgrade that weld metal a little bit to get you some better corrosion resistance. Next slide. So one of the first places that was really used in industry, which I believes goes back to the 70s in the United States, was the municipal waste burners. Historically, these water wall tubes were made with a low alloy steel, something like a 2 1/4 or 1 1/4% chrome alloy. And that worked fine under most situations. Then we started burning some of the municipal waste. The fume and the byproduct got much more corrosive. And as you can see in the picture, we started seeing very quick erosion and corrosion rates on these steel tubes that were causing some serious problems. So one of the solutions was to go back into those existing plants and just clad the entire water walls with the nickel alloy that gives much better protection compared to the steels. Where that's commonly done in a vertical down MIG process, as you can see the piece of equipment on the right, which is very a quick weave back and forth vertical down to kind of just cover, but a very thin layer of nickel over that alloyed steel, which just really gives it substantially better corrosion protection. Next slide. Another very commonplace popular area for Inconel 625 was in the oil and gas extraction industry. A lot of the different low alloy component pipes and valves were clad with 625 to just really protect and extend the life of those valves, where if you made the whole thing out of steel, you'd start seeing some pitting and some corrosion very quickly around some of those seal components, which would cause them to fail very fast. The other requirement that came out of this was NACE MRO 0175, which actually puts a limit of iron that's allowable at the surface on these nickel clad welds, which really led to the development of a low iron Inconel 625, which is pretty much the standard for the welding filler metal now, which is at best is going to only have a 0.5% iron in that wire, but that just really helps you minimize the iron dilution or minimize the iron level at the edge of that clad surface, and you just have more nickel and less iron, and therefore more corrosion resistance. Next slide. Shielded metal arc cladding with Inconel 625 is still done commonly, particularly on elbows and different pipes that have an odd shape to them, where it may not be practical to reach in with a MIG system or a TIG system. One of the other things that's not really thought about, where the shielded metal comes as a big advantage, if you notice on this picture on the left, that's a very thin-walled steel type tube. It's probably only about 3/8 of an inch thick. So the fact is, if you were really putting a lot of heat and going quick, you'd probably deform that, and you'd end up with some kind of not round shape by the time you're done with it. So just the nature of the shielded metal being a slower process just allows for that to hold its shape a little better, and allows you to clad on a thinner surface than you could with some of these other processes we'll talk about here in a little bit. One of the other big applications in the United States was the high chromium, 30-ish type chromium nuclear alloys. Historically, a lot of the welds on the nuclear power systems in the United States were welded with an Inconel 82 or a 182 electrode, which is anywhere from about 14% chrome all the way up to maybe as high as about a 20%. But that was still causing some problems with the stress corrosion cracking down the line in these components. So the second generation bumped up the chrome level, as you can see, to about 24 to 26%, with some of the latest alloys closer to the 30% chromium level, which basically just really minimized the crack growth from stress corrosion cracking. That was a big problem in those reactor components. Next slide. So as you can see here, this is a structural weld overlay, which was done not so much for corrosion on the outside, but as you can see, these safe ends were a pretty elaborate amount of different alloys and different welds. You can see on the bottom, there's a low alloy steel that had a stainless layer of weld metal, then a nickel alloy, then you had a stainless steel safe end, and some other components. With all that dissimilar welding going on, there was a very high probability or problem for stress corrosion cracking. One of the simplest ways to mitigate this was to simply cover that entire weld joint with a much more corrosion resistant alloy like an Inconel 52M or 52MSS that basically just covers the entire weld and basically eliminates that potential problem. Next slide. Along in those same alloy groups, you've got a lot of components that were entirely clad with the 52M and the Inconel 52MSS, done with multiple processes. One of the most efficient we'll talk about here is with weld strip. With weld strip, you're kind of putting, instead of a single point, which you would have with a wire, you've got a much wider strip, so you're covering a lot more area of a component. That's a big advantage as far as a time saver. But you introduce some things like a lot more heat input, a lot more other nuances that can cause some problems. I believe this is the actual reactor dome lid that'll be clad with 52 or 52MSS, or 52M, excuse me, and 52MSS, and then it will be formed into the dome that actually protects the reactor. That alone causes some other issues, which we'll see in the next slide. So the other big advantage to doing that is tube sheets. You know, the tube sheets come in contact with some of the more corrosive media in a reactor or in just a heat exchanger in general. So when you're cladding for a tube sheet, you run into an additional problem. All of a sudden your weld metal, after you've put all that clad down and machined it, it's now the base metal. So it's got to be pretty much held to the same standards you would as a base metal. So one of your challenges becomes keeping that sulfur in that weld metal incredibly low. So you could take one option of using a gas shielded process such as TIG, and you're going to end up with the same amount of sulfur you started with in the wire, essentially. That's where you see the nickel base metal with the sulfur less than 0.001. You know, the weld metal from a gas process would also be around 0.001%. One of the downsides, as you see to that, is your deposition rate could be anywhere from as low as 2 pounds an hour to maybe, if you're really pushing a hot wire process, you might get up towards of 16 pounds an hour. Whereas if you can go with the strip cladding, you know, you can be as high as 30 to 60 pounds an hour. So we can be much quicker. However, you do run into the problem of picking up some of that sulfur from some of the other flux-based components on there. And the reason that's kind of a particular problem with a tube sheet is you see on the picture in the left, when they're welding these tubes up, you essentially already have a notch or a crack right built into the joint design. So you really need very low sulfur to just so you don't avoid taking that crack and having a solidification crack run right up you know, into the weld where you already had a predetermined notch essentially in that weld. Next slide. Superheaters is another area of a lot of concern. In the United States, there was a Clean Air Act initiated in 1990. A lot of the other world started, parts of the world started a little earlier, some a little later, but the overall effect and reason for this was to reduce pollution. So what we want to do, instead of letting a lot of these nasty components out into the atmosphere, we wanted to capture them and keep them maintained in the power plants. The downside to that is you're now keeping some very corrosive materials contained in the power generating system, which can concentrate and become very corrosive very quickly. Lew will talk a little bit more about that later, but once these low NOx burners were put in place to reduce emissions, you started seeing some very aggressive corrosion rates in a lot of these materials. Next slide. So this was basically an experiment that was created at Special Metals with some the salt and metal chlorides to basically illustrate how, as these reactions take place in the plant, they kind of concentrate and condense the nasty materials, your chlorides and your other halides, into a very aggressive media that's much more concentrated than it would have been in a normal situation. As you can see on that tube sheet, there's some pretty severe corrosion that's happened on the edge of that pipe due to the concentration of these melted salt deposits. So in addition, in an effort to kind of look at some new alloys, they created that experiment and then ran some tests with a wide variety of different nickel-based alloys. And you can see you had corrosion rates anywhere from substantially pretty high attack down to the newer filler metals such as the 686 CPT with incredibly low attack rates. But this is just a very good illustration of some different corrosion rates and different alloys that have been used on the superheater locations. Next slide. This is another example of some experience that Special Metals had with some Inconel 72 on the superheaters. And as you can see in that picture, obviously the tube that's shown up front was blasted and cleaned up a little bit, but you had some pretty heavy deposits of this melted salts, if you will, depositing on these superheaters. But after 7 years of service, you know, very little or no attack on the Inconel 72 tubes. And there's well, just one quick mention on that. That pattern is a very specific process that's used to clad these heat exchanger tubes, which is, depending on who's doing the work, it could be a combination of TIG or MIG, but there's a lot of different nuances to really minimize the dilution and then therefore minimizing the amount of metal that needs to be deposited on those tubes. And that has that's probably a whole series of lectures on its own to really get into the nuances of putting down the smallest amount of metal that still has the corrosion resistance that people want. Next slide. One of the last little nuances that was discovered with kind of one of the new Inconel 72M filler metals was the electrical resistivity. Obviously, the reason we're going for these upgrades to these plants is to get more efficiency out of a given plant. So with the Inconel 72M, you actually have a very interesting phenomenon happening during the service life of that alloy. Meaning, as it's deposited, you have a electrical resistivity of about 1.2, I believe that's micro ohms per meter. But as that alloy sits in service and actually experiences higher temperatures, your electrical resistivity actually goes down over time. And why is that important? As you can see on the second bullet point, electrical resistivity is inversely proportional to the thermal conductivity, which that basically means the longer this alloy is in service, the better the heat transfer is in this alloy and the better the efficiency is of the power plant. So that was kind of a very interesting nuance that popped up, but it was a very big advantage to some of these newer alloys as far as cladding, not just to protect the existing system, but to actually increase the efficiency of it. Thank you for your time. We'll be addressing questions at the end.
Okay, thanks, Brian. And just to go over some of the details, I see Sam was starting to answer some of the questions in the chat. There is actually a Q&A function on there if you look at your menu. So I already see there's about 52 comments in there. So try and keep all your questions in the Q&A section instead of the chat. At least in the Q&A section, we'll be able to address those specifically. And as we kick into this next presentation, our presenters will go through that Q&A section and try and address each one of those questions. We'll still have the Q&A session at the end of the presentations, but try and keep your questions in the Q&A menu, and the presenters will start going through those, answering those, and we'll pick up from there. Any of those that have not been answered through type, we'll start going through those once we're done with the presentations here. So looking at the next presentation will be cladding nickel alloys. Or did you go over that already, Brian, in your last presentation, or is that just the joining section? That was the first
that was both of them put together.
Okay.
So we'll be on
okay. All right. Okay, Luke. Then we'll be going on to the corrosion testing and FGD then with your side. Just bring that up. Okay. All right. Over to you, Lou.
Thank you, John. Well, good evening, all. This evening, I'd like to talk to you about flue gas desulfurization systems, or FGD as they're more commonly known. First, we'd like to look at the system and discuss what they do. Then we'll look at how the system is designed, the corrosive conditions that exist in these types of systems, and why we use nickel alloys, both base metals and welding products for their construction. And then finally, we'll look at some corrosive attacks that we've encountered and how they were addressed to provide longer life for the systems. An FGD system is an air pollution control set of components that are designed to remove sulfur dioxide from the effluent that results from burning high sulfur coal for generating electric power. Next slide, John. The most commonly encountered type of FGD system is a wet lime limestone system where a slurry of ground limestone or calcium carbonate is mixed with the effluent from the boiler. The SO2 reacts with the calcium carbonate to form calcium sulfate or gypsum. This precipitates out of the wet system and can be collected and disposed of. Actually, It can be used for producing construction board and road aggregate. So there is a use for the subproduct of that reaction. The next slide. This shows the corrosive nature of the various components within the FGD system. The reaction tank, where the gases are mixed with the slurry, because of the wet nature of that, it's only moderately corrosive. But the drier parts of the system, where there's condensation and formation of acids, are much more aggressive. These are the red zones. So the inlet duct, the outlet duct, and the chimney flues are the areas where we most often encounter corrosion and where the higher nickel alloys are required. The next slide, John. This is an example of what can happen when inadequate materials are used for construction of the system. These are two scrubber vessels that were fabricated from 316L stainless steel. After about a year of service, you can see the result. There's leakage of the material from inside the vessels coming down the outside, so the walls have been completely perforated by corrosion. And you'll also see some smoke up at the top there. That's not supposed to be there. So again, that's the result of leaks caused by perforation of the 316 stainless by corrosion. The next slide shows some of the type of corrosion we see. Typically, the corrosive mechanisms encountered in FGD systems are of the localized type. Pitting corrosion, as we see here, can be a very dangerous type of corrosion in that while the general corrosion rate of the material may be very low, the pit, once initiated, can bore its way all the way through the complete section, causing a leak very quickly. And the next slide, crevice corrosion is another more aggressive type of corrosion, actually more aggressive than pitting itself. We sometimes refer to this as under deposit corrosion because in the FGD systems, a mineral deposit can form on the wall. Underneath that, the micro environment can be very aggressive. Brian showed a slide of a boiler tube with a deposit there and how the halides, chlorides, fluorides, whatever, can concentrate below that deposit. We see exactly the same thing in FGD systems. So under the deposit, it will be high chlorides, high fluorides, and very low pH, which results in very, very rapid corrosion. The next slide shows just what happened in some operating scrubbers. Between 2000 and 2006 in the USA, there were 84 FGD absorber vessels fabricated from grade 2205 duplex stainless steel. And all of those failed by perforation, by corrosion in less than 2 years. And in most cases, the attack was even more rapid than that. Some failed in as little as 6 months. The picture on the right shows the type of corrosion we see. The weld itself there is Incal ferrule metal 625. And you can see there's no corrosion of the weld itself. But these welds are actually standing rather proud of the base metal, so they were a place for the deposits to collect. So once the deposit formed, you can see what happened underneath. There's very, very aggressive crevice corrosion. The next slide. This slide shows another case of crevice corrosion. In this case, this is a manhole cover. Again, made out of 2205 duplex steel. There was a rubber gasket used to seal the manhole cover to the manway, and you can see that ring of corrosion that exists in the center of the cover. The gasket acted like a tight crevice, and the crevice attack formed under the gasket. The next slide. There's been basically 3 types of construction that are used for building FGD equipment utilizing nickel-based alloys. They can be solid alloy plate, In that case, welding would usually be done by either shielded metal arc welding or gas metal arc welding in the pulse mode of transfer. A way to reduce costs is to use alloy clad steel plate. And in this case, the steel part of the clad plate acts as the structural member of the system, and the alloy cladding, which is typically maybe 1.6 millimeters thick, protects the structure from the aggressive corrosive environment inside the system. Another way to do that is with sheet cladding. Again, Brian talked about weld cladding. That can also be done by welding alloy sheet over top of a steel structure. Wallpaper is the typical term used for that. But this would be alloy sheet on the order of 1.6 to 2 millimeters. In North America, we typically use gas metal arc welding for that purpose. In Europe, they tend to use gas tungsten arc welding. So I guess it just depends on what your welders prefer and what they're most adept at using. These next few slides show some of the components that have been fabricated for FGD systems by these various techniques. These are two chimney flues that are fabricated from Inconel 625 plate. This chimney is about 1,250 feet tall. So you can imagine there's a lot of expansion takes place in a structure that long. So at the top of the flue on the right, you can see an expansion joint that's used to offset that expansion. The next slide shows the expansion joints that are fabricated, again, from solid alloy 625. They were built in two pieces and then assembled into the system. The next slide shows how the chimney itself was built. All the welding was done on the ground. Pieces of plate were rolled into the shape. I think there were 3 plates per ring. They were welded together, and then a large crane picked up the existing chimney. The ring was slid under there, welded together, and they progressed that way so that all the welding was done from the ground. That's not the only way that could be done. The next slide shows an alloy clad steel chimney flue. This is alloy C276 clad steel, and they welded that from a float that moved up and down the center of the chimney. The welding procedures for these, though, are very similar. Solid alloy welding materials, both for the solid alloy and for the alloy clad steel plate. The next slide shows an outlet duct that was lined with alloy sheet by the wallpaper technique. This is alloy 22, 1.6 millimeter sheets. They're about 48 inches wide and about 120 inches long. And they were attached to the steel structure to protect the material from the aggressive environment inside the duct. You can see some plug welds in the center of the plates that are used to reinforce the attachment of the sheets to the steel structure. The next slide shows a similar type of construction. This was an FGD absorber vessel. Originally, it was planned to rubber coat the vessel. It was fabricated from steel and it was going to be rubber coated. Unfortunately, when it came time to install the rubber, they couldn't find a group that was satisfactory for the job. So they redesigned and decided to use alloy C276 wallpaper. And it was installed very similar to the duct you saw earlier. About the same size sheets, and plug welds, again, were used to reinforce the attachment of the cladding to the wall. The next slide shows that cladding is not the only thing that can be done with wallpaper. Here was a case where a damper blade had corroded and it either had to be replaced or repaired. The repair was accomplished by welding 1.6 millimeter sheet over top of the existing damper, again by the wallpaper technique. So that way, instead of replacing the damper, it could be repaired and put back into service quickly. This slide shows the the various techniques that can be used for wallpapering. The objective here is to be sure that the service weld is not exposed to iron dilution. In the first scenario, you see the sheet has been welded to the steel substrate, and that weld obviously will be diluted with iron. But the next weld, the sheet would overlap the existing sheet, and that weld would be an alloy to alloy weld. So the service weld is not diluted with iron. The next two scenarios show how a batten strip can be used to cover the diluted welds. In the number 2 technique, you can see 2 sheets are welded to the steel substrate. Those welds would be diluted, but then a batten strip of the same alloy is welded over top of those welds, and those service welds would not be diluted. The situation number 3 is just basically the opposite of that, where the batten strip itself is welded to the steel substrate. And then the next 2 sheets overlap the batten strip, and those welds again would be not diluted. The next slide gets into material selection. The schematic I showed you earlier showed the various sections, and we had green sections that were moderately corrosive and red sections that were severely corrosive. In the moderate section, and this is usually the scrubber vessel itself, some of the advanced grades of stainless steels have been used. These are the superaustenitic stainlesses that are modified with nitrogen. They typically contain about 6% molybdenum, and we make 2 of them. One is called Nickel Alloy 25-6MO, and the other one is 25-6HN. We also developed an advanced grade of superaustenitic stainless that's called Nickel Alloy 27-7MO. While it's only slightly more highly alloyed than the existing products, the corrosion resistance actually approaches that of alloy C276. Yet the cost of the material is only about 60% of that. So here's a case: if you can use these products, their cost is considerably lower than a higher nickel alloy. But in the severe areas, the outlet ducts, inlet ducts, and the chimney flues, those just almost always have to be fabricated from a nickel base chrome moly tungsten type alloy. Alloys like C276, 22, and Inconel 686 is our most highly alloyed, most corrosion resistant material. And it has found applications within FGD systems. The next slide shows some of the chemical compositions of some of these materials that are used. I would draw your attention to the molybdenum content. For resistance to localized corrosion, usually it's the molybdenum content that determines the corrosion resistance of the material. So if you compare something like 316 stainless, we saw the scrubber vessel that had corroded very quickly. With only 2% molybdenum, it doesn't have a lot of corrosion resistance to localized attack. Whereas the higher alloys at the bottom, 22, C276, and 686, have 14 to 16% molybdenum. And if you'll note, they also contain 3 to 4% tungsten. And tungsten has an additive effect with the molybdenum. So the relative resistance to localized attack is the combination of those two elements. So obviously they have much greater resistance to localized attack than the lesser materials. The next slide just demonstrates how much the corrosion resistance of these materials can differ. This was in an outlet duct in a power plant in Florida where it was very hot. The duct was originally fabricated from alloy C276, but due to a leaky damper, there was quite a bit of leakage of the acidic environment into that duct, where it became very hot and it was attacking the C276 very quickly. We installed a 4-sample test piece with 4 alloys to see how they would perform. The upper left-hand sample is alloy 686. The other 2 that you see adjacent to that are 22 and C276. In the lower right-hand corner, there was a sample of a superaustenitic stainless steel, ink alloy 25-6MO. After 6 months, you can see that that sample has completely corroded away. In this case, the 686 was not corroded, and there was initiation of localized attack in the 22 and the C276. So I guess the message that we could conclude from this is that a higher alloy provides much more corrosion resistance than a lower alloy. In this case, a thin section of 686 would have provided long-term service, whereas a heavy section, these samples were 6 millimeters thick. But if you had used 6 millimeters or 8 millimeters or 10 millimeters or whatever of the stainless steel, the life would have been still very short. So it just shows that a higher alloy, when it's required, even in a thinner section, provides much better resistance. The next slide shows another way that materials can be evaluated for FGD systems. In this case, it was a laboratory study. This is a very aggressive environment, obviously, but we estimated that it might be similar to what would exist in under a deposit in an operating system. Very acidic with halides present. You can see the results. We tested an austenitic stainless steel 316L, 2 duplex, the 2205 duplex and 2507 super duplex, and then 2 austenitics, 6 millimeter or 6 moly super austenitic, our advanced grade 277, and then a nickel-based alloy C276. You can see there's a 37 mil per year corrosion rate on the 316, which is obviously too high for a long-term service, and would pretty much agree with the results we saw with those 2 316 scrubbers I showed you earlier. But look at the 2205 and the 2507. Those samples have just basically corroded away, and this is only after a week exposure. The super austenitics and the C276 all exhibited low corrosion rates. The next slide, I would caution you that some people have tried to use existing corrosion tests to compare materials for FGD service. And this is a misapplication of the test, and it just simply doesn't work. The next slide shows the general corrosion rates that you see with an ASTM G28 method A corrosion test. The corrosion resistant alloys and stainless steels have to be in the right condition to provide their optimum corrosion resistance. They have to be annealed properly, and they have to be cooled properly after annealing. The G28A test is designed to verify that products have been properly heat rate. And when you're testing material, you compare that, the rate you get to the base rate alloy. And if it's, you know that it's been properly heat treated. But if you try to compare alloys to each other, you'll get erroneous results. If you notice, C276 has the highest rate of any of the materials in this list. In fact, the 3 highest are the 3 most corrosion resistant materials, nickel, chrome, moly, tungsten materials that we know work very well in FGD systems. The 3 lowest rates are 316L, a super austenitic, and alloy 625, and we know that these materials do not have nearly the corrosion resistance of the nickel chrome molys. So you can see you get erroneous results by trying to use that type of information. The next slide. The ASTM G48 test, which looks at localized corrosion, has also been tried. And while it might be a little bit better test than a G28 to compare materials, you can still get erroneous results. The G48 test is conducted in a solution of 6% ferric chloride, which is a very highly oxidizing salt. The next slide shows the results of two nickel-based alloys and why this test is not really valid for what we're talking about. The oxidizing salt, ferric chloride, is quite different from the environment within a FGD vessel. Typically, the media inside an FGD system will be reducing. So the oxidizing nature of the ferric chloride is somewhat different. In general, materials with higher chromium provide better corrosion resistance to oxidizing salts and acids. So the alloy 22 with 22% chromium does indeed provide better resistance in this test to the crevice temperature for degrees C compared to C for alloy C270. In a very similar manner in FGD environments. So obviously you would be misled if you tried to use these results to compare these two materials. Your material. Next slide, please. There we go. Nickel chrome moly corrosion resistance and alloys are fairly complex materials. The elements that make them up can form second phases if they're not properly processed, which can deteriorate the corrosion resistance as well as the mechanical properties and fabricability of the materials. We see mu phase in the nickel chrome moly alloys. Some of you may be acquainted with sigma phase in some of the other alloys and stainless steels. But the presence of these secondary phases is definitely deleterious to the properties of the material. So my suggestion would be, if you're using these materials, stick with the ASTM specification for the chemical composition. We've seen cases where customer has asked for increased molybdenum content or different variations on our standard composition with the idea that they think they can improve the corrosion resistance. But the fact is, if, for example, C276 or 22 or 686, if the molybdenum gets too high, then you start precipitating U phase, which actually decreases the corrosion resistance. So leave the chemical composition to the existing specs and the experience of the metal manufacturers. The next slide. Obviously, if we're building these systems out of corrosion resistant alloys, we want the welds to be as corrosion resistant as the base metal. The nickel chrome molybdenum welding products can suffer from the effects of elemental segregation during solidification. Molybdenum and tungsten melt at very high temperatures. Thus, when a weld is solidifying, those materials, those elements are the first materials to solidify. So that's part of the weld that solidifies first, will be enriched in molybdenum and tungsten, whereas the material that solidifies last will be depleted of those elements. So you can see some variation in on a micro scale, actually, across a weld due to these elemental segregation effects. The best way to offset that is to use an overmatching composition welding consumable. Typically, stainless steels, the superaustenitic stainlesses, and some of the lower alloys like 904L have been welded with filler metal 625 or filler metal 622, both being overmatching in composition to the base metal. For the other nickel chrome alloys like alloys 22 and C276, we suggest the use of IncoWeld 686 CPT welding consumables. So in this case, even with elemental segregation, with our higher alloy content, you still get a weld that is matching or even overmatching the corrosion resistance of the base metal. The next slide shows what can happen if you don't use an overmatching composition weld. This is that same duct that I showed you earlier where we exposed the 4-sample test. This is alloy C276, and you can see the weld is just almost corroded away. This was welded with a matching composition filler metal, and the weld has just basically lost all of its structural integrity. There's certainly attack of the base metal as well. The next slide shows, in an attempt to repair that, the weld was replaced with filler metal 686 CPT. And after 6 months, that weld is in good shape. We're not seeing any corrosion there, but the base metal is continuing to corrode. So based on the result of the 4-sample test that we exposed, plus the performance here of the 686 CPT filler metal, that duct was relined with alloy 686 sheet, welded with 686 CPT filler metal, and the corrosion stopped. The next slide. In Brian's presentation about cladding, he mentioned iron dilution, and we can encounter that same problem in FGD systems if we're welding alloy clad steel plate or in the wallpapering technique. In either of those cases, there's potential for dilution of the weld with iron from the substrate. To avoid that, obviously we want to use a procedure that minimizes the iron dilution, but if it does occur, we would suggest the use again of an overmatching composition filler metal to counter that iron dilution. That way, even with if some iron does get into the weld, it still has full corrosion resistance. So just to kind of summarize the next slide, what does it take for a successful FG design and fabrication? Obviously, we need to understand the corrosive conditions that exist within the system and the requirements of service. Based on that, we need to make the proper alloy selection for the specific environments in each of the components of the system. And obviously, we need to choose a welding product and process that would deposit a weld that will have good corrosion resistance for the environment. We mentioned, discussed 3 construction scenarios. All of those have been successfully used. Basically just a matter of choosing the one that's most appropriate for your system and for which you have qualified welders. During the fabrication operation, proper oversight and adequate quality control is an absolute necessity. Welders should be qualified for the welds they're going to make, and certainly each of the welding procedures should be qualified as well. Once the system goes into operation, you need to be sure that the operating conditions are within the design criteria. We've seen cases where FGD scrubbers were operated out of control, and corrosion can occur very quickly. So operate the systems as they're designed. And the problem of crevice corrosion, I mentioned it's probably the most aggressive type of corrosion we encounter. Takes place under mineral deposits, under deposit corrosion. So if you can operate the system so that those mineral deposits don't form. For example, the weld I showed you in the duplex steel stood proud of the base metal. Make sure the welds are not that high. If you can avoid the mineral deposits, you'll go a long ways to improving the life of your system. So obviously, the next slide completes my presentation. That we need clean air and clean skies, and by the use of operating FGD systems, we can control the pollution that comes from burning high sulfur coal for power generation, but still maintain a clean environment. So that concludes my presentation. Thank you for your attention. And now I think we have time for some questions and answers.
Yep.
Krishna will take over. Dr. Krishna will have a session, question answer session. Krishna?
Mr. Girotra, I would request that by the time, John, if the team can decide which questions to take, in the meantime, if we have Mr. Ernest with us, if he would like to share a few words while you choose the questions which they would like to answer, because the questions are about 83. I'm not sure if we'll be able to get through all of them, but it was a brilliant session, and that's why so many questions. So I guess if we can get Mr. Ernest to say a few words while you choose a couple of questions each, and maybe we can answer them.
So we're extending it. We're extending the session by how many minutes? 20 minutes, 15 minutes?
As long as people are there, Mr. Girotra, it's not a time session. Let the people be there, and as far as they are comfortable answering a few questions, we can take them, and then we'll move it forward.
Good, thank you. So let Mr. Ernest say something.
Okay, very good. So thanks, guys. I'd first of all like to thank you for your kind attention. The guys were really excited to do this this seminar today, and I think we shared a lot of different information. There's a lot of questions, so we certainly will stay. We'll certainly take a few questions after this, and I think if there are any left over, Mr. Girotra, if you can send us the questions, we'd be happy to go through them and answer them afterward.
Yeah, good. We will do that.
Then we can share it with all the members.
Right. You know, I don't want to keep everybody too much. I know we're over time. We got a little trouble getting started, so I don't want to sort of impose on everyone else's day. But at the same time, I think it would be good if we could stay. We certainly would like to stay and answer a few questions.
Yeah, what we can do is maybe we can select few questions which may be even common. Many questions may be common. So we can select a few and we can answer that, and remaining we can get it clarified through mail.
Yeah,
which
go
we
ahead.
can share with all.
Okay. So
Continue.
So I mean, I guess Sam, Brian, Lew, do you guys have one that you've seen that you'd like to get started on?
I got them. Well, unless you guys got it, I can see all the questions right here. I was just going to start going through and picking a few of them, sort of randomly out there.
That would be better.
Just so we can. Okay.
There was one about welding duplex stainlesses or super duplex stainlesses with nickel alloys. And the asker had a pretty good thought, excuse me, because duplexes and super duplexes typically have quite a bit of nitrogen added for enhanced pitting resistance. It is better to select filler metals without niobium, because niobium has a strong affinity for nitrogen. And when you have niobium nitrides formed, the areas in the matrix around those precipitates typically will be poor in both niobium and nitrogen, and they can be attacked. Also, you can form a continuous line or almost continuous line of particles or precipitates that will contribute to bin test problems. So we do recommend niobium-free materials, Inconel filler metal 622 or IncoWeld filler metal 686 CPT for welding those high nitrogen materials, and not just the duplexes and super duplexes, but all of the high nitrogen materials used in corrosion resisting applications.
Thanks, Sam. So I was looking through the list, and a lot of the questions are kind of in depth, and it'd be kind of hard to cover in just a few minutes, right? But I saw one which was, I thought, interesting and should be pretty quick, and that is, what is overmatching? And then I'll add on to that, why does it matter?
If I could, just basically, the weld metal is a cast structure, and most of the things we're welding on are wrought. Wrought materials have a good homogeneity of elements throughout them because they've been hot or cold worked and then annealed. The weld metal is always in the as cast condition, either as cast or stress relief. And so when you have an as cast structure, you have depending on how hot you're welding and the cooling rate, but you always have a somewhat segregated weld deposit. And so the reason that you need an overmatching product is so that in the segregated structure, you have both high levels of corrosion resisting elements and low levels. And so you want the low levels of corrosion resisting areas in the weld metal to be higher than anywhere in the base metal. So that's why you need overmatching materials, weld materials.
What about strength, Sam?
Strength, sure, you'd like to have the weld to be slightly stronger than the surrounding base metals. And some of the other guys can kick in too, if they'd like.
I'm actually trying to knock out some of these shorter, quick questions by simply typing them. If it's, a couple sentence answer, I'm trying to get them out pretty quick if possible.
I've been doing that too, Brian.
So Brian, can you just pick one that you're working on and share it with everybody in the audience?
Yeah, actually, this has been at least 2 or 3. A lot of the questions are asking about like a post-weld heat treatment, particularly on something like a P22 or a T22 material, which is the the 1.25 chrome low alloy steels. You will still need to do the post-weld heat treatment to get the strength and correct the microstructure of that alloy, even if you weld with the nickel alloy. The big advantage of using the nickels on though versus say a matching material is the nickel alloy will not be affected by that post-weld heat treatment. So for example, with say a nozzle that requires a post-weld stress relief to get rid of some of the inherent martensite that would be formed by welding, you could weld a section of nickel onto that valve or that component, do the post-weld heat treatment to get that component, microstructurally sound, then the nickel would not be affected by that. So then you could go back and in service weld, that component onto another component where the nickel is the only affected base metal by that weld or by that second weld. And it allows you to attach those components without having to do a post-weld heat treatment after welding. But if you're welding anything that normally requires a base metal that requires a post-weld heat treatment, even if you use a nickel, you're still going to need to do that for the most part. But that nickel won't be affected. So that gives you a lot of other flexibility, in staging your heat treatments and then attaching components at a later time.
Maybe just a quick comment. Maybe the statement that we made in Different but Not Difficult might be confusing. What we were talking about when you're welding in a solid solution nickel alloy with a matching or a similar weld material, that does not require a post-weld heat treatment usually. In the case where it might be subject to intermediate temperature service, like between 1,000 to maybe 1,300 or 1,400, you may have to give it a post-weld stress relief in order to avoid SRC or I'm trying to strain-related cracking in service. So the post-weld stress relief would be to remove that. But in general, the solid solution nickel alloy base metals and weld metals do not require post-weld heat treatment. But what Brian said is exactly right. If the base metal requires it, then you need to do that. You have others, Ernest?
Sure. I mean, so I'm looking at one here. It says, how do you distinguish the nickel oxide from normal nickel surface, right? You can't see it necessarily. How do you know whether you should grind or do some treatment to it?
I tried to address that, but maybe it wasn't clear enough and not enough. And typically, as you're welding, and all of the welders out there will identify with this, you can see little oxide islands floating on the puddle. And they often float over and attach themselves to the weld near the sidewall. And basically, once you lift your hood and you clean with the wash a little bit, if you look carefully, you can see there's a difference in topography where the oxide has floated on the weld metal. So it will be slightly higher than the actual weld metal. If you have that situation, you need to grind to remove them. If you have so many oxides that are completely crusted over, you definitely have to do complete surface removal by grinding. But generally speaking, per each bead, if you have one bead, you can see the oxides floating on top. And typically you can, after you've finished, you can see the difference in altitude actually, or in depth. The weld metal will be below the surface of the oxide.
Okay. So Lew, I guess I have one question for you, and I see a number of questions in here about corrosion resistance and comparing like an iron-based alloy to nickel-based alloy. We can't go into the sort of science of it today, but I mean, generally speaking, what's the difference in treatment, I guess, in your experience between welding or using nickel-based for corrosion resistance versus maybe a stainless steel, one of the more common stainless steels?
Please switch on your mic. Please switch on your mic.
Ernest, I think you'll normally find that the nickel-based alloys are more corrosion resistant than stainless steels, simply because of their higher alloy content. For example,
one of the questions the asker sort of claims that certain stainless steels have improved localized corrosion resistance. Do you have any experience with that?
Yes. For example, 316 to 317 are the molybdenum-bearing stainless steels that are commonly used in environments where you would expect localized corrosion. Alloy 904L is another of that class. And they work well if the conditions are not more aggressive than those materials will tolerate. But in many cases, like in an FGD system, in seawater, in more aggressive environments, then something like an alloy like 625 up through the C alloys and to alloy 686 would be required. So it just depends on the environment that they're exposed in. A more concentrated environment is usually more aggressive. And as the temperature goes up, higher temperatures usually result in higher corrosion rates. So if it's a low temperature environment with low concentrations, 316 or 317 or a stainless steel might be used. If it's a higher temperature and a more aggressive environment, then the nickel alloys would be required.
Okay, looking through, found another one. I guess I'll direct this to you, Brian, unless anybody else wants to chime in. While joining 625 stick weld, flux is very sluggish and basic in nature to avoid hot cracking, but it leaves tiger strips in the weld. How do I minimize that?
When you're talking of tiger stripes, I'm assuming they're meaning like the areas where the slag actually cracks. I don't want to say prematurely, but a little sooner while the weld's still pretty hot. Typically, the biggest problem with that is actually weld bead shape. If you're kind of running a quick, say like a stringer bead, where there's a lot of the aspect ratio is pretty tight, that slag can lift up pretty quickly. And I don't want to say too fast, but it can actually lift up where the weld metal is still very hot, and you get a bit of like a gold tint where oxygen just got onto it a little quicker. It's kind of difficult to remove because, you know, as a manufacturer, most of the time we really want that slag to almost, you know, self-peel and lift off very quickly. But there are situations where that can almost happen too fast, and it creates those tiger stripes. Typically, the main solution is going to be to kind of change your weld bead ratios a little bit to get that slag a little more thicker and wider, so it doesn't lift as easily. But the other side of that is if you can, you know, if you're getting the tiger stripes, that means the slag is coming off pretty easily. So it's, you know, not always necessary to change your technique and your bead shape just to avoid that. When it can be, you know, a very light grinding can kind of take care of that oxide color. So to avoid that, you may end up causing a lot more problems by, you know, telling your welder to change his bead shape and everything else. It's not going to really make him comfortable. It's one of those things that if it's, you know, a minor heat tint or a, you know, a bead color, you do want to remove it before you get into a corrosive nature, because that's another crevice that can increase corrosion. But it's often easier to just do a light grind or something versus completely tell your welder how to change what he's doing just to avoid a minor inconvenience as far as a discolored weld bead. That's assuming you're not getting, you know, gross, you know, porosity or something where that slag's removing very quickly.
Ernest, I saw one appear just a few minutes ago. A gentleman asked about welding 320 with 112 and 625 instead of the 320 composition. And we have had quite a bit of experience with that in the past. And basically, you often run into 320 LR, which is low residual. The 320 composition itself is so fully austenitic, it has no ferrite, and so it tends to be crack sensitive just on its own. And so that's why the low LR, the low residual, they're trying to keep it from cracking. But by the time you've gone through all of that and trying to keep it from cracking, oftentimes the cost of that material is even higher than Inconel 625 or Inconel 112 electrode, which is substantially over-alloyed for the 320. So because of the volumes of 625 and 112, the cost of 625 and 112 is an absolute bargain compared to what you pay for the low alloy or the low residual 320. So essentially, the 112 625 is always a better buy.
Yeah, that's a real good point. And another thing to just mention to that, Sam, is you have to be very meticulous when welding the 320 LR, whereas 625 is very robust. You can kind of just put it down there and it runs. So it's, I mean, other than the cost savings, your headaches that are the less headaches for the welder and difficulty for them also get you a lot of gains with that as well.
Yeah. Good thought, Brian. True. And the cost savings with the 320 LR are really not that great when you get down and looking at it.
Okay, I see one here. The attendee asks what controls, and specifically states welding parameters, need to be taken during cladding with alloy 625 to maintain iron content within acceptable limit. So what do you all think about that?
I'm sorry, I didn't hear the details of the question.
I'm
Could
sorry.
you repeat
so,
it?
So the attendee is asking what controls need to be taken during cladding with alloy 625 to maintain iron content within acceptable limits. So it's like an iron dilution question, right?
Sure, absolutely. And if you recall the slide that Brian showed it had the big harness over top of it that was controlling the cooling rate for the base metal's sake. But basically, that was all done with pulsed gas tungsten arc welding, which I don't know. I don't think Brian mentioned that photo was courtesy of Arc Specialties down in Houston. But they have a procedure where the pulse gas tungsten arc welding process with 625, they can get 2 to 3% dilution in the first layer. And so that's excellent. That's what you need. I mean, that's what you'd like to have. If you get to around 5%, you're still pretty good shape. But one of the problems, and I've answered this in typing, one of the problems with 625 on steel, and I've heard people even say, oh, we don't recommend 625 sub-arc on steel because it cracks. Well, it does crack if you get too much dilution. And the reason for that is the lavage phase. If you get too much iron dilution into a material that has 3.5% niobium, you form lavage phase and it tends to hot crack. So the key to good corrosion resistance and good welds, solid, not having any cracks in it, is keeping the dilution low. And with pulse gas tungsten arc automatic, even with hot wire, you can get 9 or 10 pounds an hour at low dilution. So that's really the answer as far as I'm concerned.
Okay. So here's another one, kind of a generalized question. How do we control the hardness in alloy 625 welding in general?
I can offer, and maybe the other guys want to fill in too, but the hardness in 625 is generally not much of a problem. It's typically maybe somewhere around between 93 and 94 or so Rockwell B, maybe to 18 or 20 Rockwell C. It's fairly low. Hardness in 625 is not that much of a problem in the asphalted condition even. So that's my thought on it. Lew, Ryan, you got anything?
Sam, that question may be related to NACE MRO 175, which states that there's a maximum hardness for each alloy for resistance to hydrogen embrittlement. But the 625, I think the maximum hardness for alloy 625 is like 35 Rockwell C. And as you noted, you're not going to see that kind of a hardness with a weld deposit, or even the anneal base metal would not even be close to that hardness. So if it were an age hardenable alloy, then certainly that could be an issue. But with a solid solution alloy like 625, that's generally not a problem.
Yep, that's my experience as well.
Okay. So here's another
question earlier about weld strength. If I could just comment briefly on that. Obviously, if it's a low temperature application, tensile strength is important, tensile and yield strength. But many of the applications for nickel-based alloys are for high temperature service, where really tensile and yield don't have much of an effect. So I guess what I would encourage people to look at is if you're using a material at a high temperature, and let's say maybe above 1200 degrees Fahrenheit, they need to look at creep and stress rupture rather than tensile strength. Just a good example of that is Incalloy 800 HT. We can weld 800H and HT with filler metal 82 up to about 1450 Fahrenheit. But above that, the 800H has higher creep and stress rupture properties than the 82. So for those applications, we'd have to use 617 filler metal. So tensile would have nothing to do with that. It's strictly, the choice would be strictly based on the creep and rupture properties. So you need to look at the actual operating temperature to know what materials to use.
Okay.
Excellent observation, Lew. I'm glad you brought it up. There's a vast difference between tensile limited and creep limited applications.
Yeah, for sure.
So we've got about 9 minutes left till the hour. I think we can take a couple more questions. I see one in here. It says, what measures should we take to ensure a convex bead always during welding? So how can the user guarantee that he always gets that?
Well, always use an appropriate travel speed, no matter what you're doing.
Yeah, that is a running joke. The majority of the problems with nickel welding that could be solved by slowing down.
Yeah,
Good
good
point.
point.
Is the number one solution to 80% I think of the problems and calls we get is just slow down a little bit.
Yeah. Slow down the travel speed, slow down the weave speed, slow down everything. But don't slow down so much that you get excessively convex bead, because then you get those tight crevices over to the side where you got to grind. But I guess the best answer is use an appropriate travel speed and an appropriate weave speed for what groove you're filling up. That's the best thing. You'd like to have the weld metal approach the base metal at the lowest possible angle and still have a slightly convex bead. And the same thing is very important to do that with the stops. I don't know how many times I've said to people, make sure you make convex beads and backfill your craters. That's important.
Okay. Let's see. I'm going to try to interpret this one a little bit. So the asker says that he's been welding 100 millimeter 625 plate and found some defects in the X-ray. Specifically, they ground out the defects, and after removal of the defect, they started welding, and they found some hairline cracks in the die penetrant test. So why is this type of crack developing in the weld? So if anyone sees cracking in the X-ray, what's maybe the top 1 or 2 reasons that they're probably getting it?
I can start if you'd like.
Sure.
I've crossed that any number of times, and typically what causes it is sometimes too fast a travel speed. If there's an iron-based material involved, you can get iron dilution, but usually you see center line cracking. And center line cracking can be so tight, it's almost impossible to see with the naked eye when you have it. And then if you don't know you have it, you just keep welding, and eventually you might stop cracking above, but you have cracks inside the weld. And that's the biggest problem, I think. And usually that comes from making either flat or concave beads in a highly restrained weld.
Okay.
Yes, and you said right there, that's, the 100 millimeter thick's pretty thick plate. There's a lot of restraint in there. The other thing that I've seen people forget is when you are excavating to do a repair, make sure your groove angle ends up being something we recommended. A lot of times people just go right after a crack or a slag inclusion and leave a very narrow bead with very high restraint, which is just a recipe for cracking. So when you're going after a potential defect or trying to grind something out, really make sure you give yourself a wide groove to minimize that stress as you do that repair, so you're not repairing a very tight groove.
Exactly, Brian. And let me add one more thing, Ernest. You don't usually see this problem, but it is a potential problem that I have seen before. With the steep sidewalls, usually when you've ground out a bead or ground out a defect, if you leave the sidewall steep and you put in a very deep, narrow bead, it'll sometimes have internal cracks, center line cracks that you can't even see from either side, and you wouldn't pick it up with die check, but when you x-ray it, then you see it. So I guess the best way to address this is that the width to depth ratio is somewhere around 2 to 1. But if you make a very deep and narrow deposit, it's like making a casting that has nowhere to feed the shrink, and it shrinks in the middle and it cracks down the middle. So you can have problems with deep narrow beads or wide shallow beads, but you probably optimum bead width to depth ratio is about 2 to 1.
Okay, well, while we're talking about it, similar question, what about pitting or inclusions? What's the most common way to eliminate that? Anybody can answer.
Good procedure, good technique. But
Okay.
go ahead. I don't mean to be a smart aleck.
Okay. Well, does anyone else have anything to add? I think we're at the top of the hour pretty much here.
I thought they were all good questions. Thanks a lot for the questions. That it shows that people have been listening and have been experiencing nickel alloy welds, and they do have real problems. And I guess if there are others left over, we'd be happy to answer those by email or later.
Absolutely.
Thanks a
Over
lot.
to you. Yeah.
Thanks a lot. The team, I think many questions answered by all three of you, four of you, and I think it's going to go great. We have about 106 more comments in, which are only in the Q&A section. And Sam, thanks a lot for reading the chat section and answering a few questions right off after your presentation. And so did Brian, do a couple of them. I think there are a lot more, and there was a lot to learn. A lot of people have gone back today, a lot richer in nickel. They would have known how to do it better. And I think the time was too short. With the amount of knowledge you guys have, we can plan a day. One day, one section, 2 hours could easily do justice to this knowledge of yours and the experience you guys have. So thanks a lot for sharing. I'll just invite Mr. Malge over to give the vote of thanks. Mr. Malge, could you unmute yourself?
Yeah, am I audible?
Yes, Mr. Malge.
Yeah.
Yes, go ahead.
Yeah. Good evening, Indian participants, and good morning to Team Special Metals. It's my privilege as a Secretary of Indian Institute of Welding, Mumbai Branch, to give vote of thanks. At the outset, let me thank the Team Special Metals, all the speakers, for having given a fantastic and educative session.
Thank you very much.
Sam Kiser,
Sam
Kiser spoke on nickel welding, different but not difficult. The topic was fantastic. It's phrased in a very well way. And he spoke on basics of nickel welding, spoke on basic differences, etc., etc. It was a quite learning exercise to most of us. Then Brian Gaal, he was with us maybe last year or little before that in Mumbai.
17.
Yeah, 17, yeah. And we traveled together and arranged some seminars, etc. His lecturers are too good. He spoke about the different processes, GPAW, SAW, joining, cladding, different processes, some practical applications. It was really educative, Brian. Then Shoemaker spoke on corrosion of flue gases, desulfurization. It is really one of the hot topics nowadays coming across, and he talked about pitting corrosion, crevice corrosion with a lot of practical examples and corrosion testing and standards. So the whole seminar was so educative, and people are engrossed in listening to that. Of course, it was not physical, but though it was virtual, but people enjoyed it. Then I also thank Mr. C.C. Girotra, Welding Specialities, and his team, who represents the special metals in India, for sponsoring and facilitating the webinar, today's webinar. I thank IIW India and Mumbai Branch organizers for organizing this webinar. I thank Mr. Kanakasabai, our chairman of the Mumbai Branch, for having taken interest into this. And my special thanks to technical team consisting of Dr. Krishnan, Abhishek Vas, and Nimesh Shunai, who organized and managed the webinar to make it success. It was a brilliant session. Thanks to everyone. Thanks a lot.
Thank you. Okay, John, Brian, Sam, for all the help you've given. Okay. Oh, here is a certificate.
This is
Appreciation.
a small appreciation from the IW Mumbai branch.
I wanted to say thank you, Mr. Garotra, the grand man of welding in India.
That's great.
I'm a bit of a numbers freak, so just to give you an insight, we had about 700 registrations to begin with, but webinars typically have a 50% hit ratio. We had about 350 people at peak who stayed around for the first hour and a half, and then till the Q&A, we had more than 250 people, and now, even as of now, more than 135 participants are live. It just shows the depth of the knowledge shared and the experience you guys have, that people really stuck around. It's a Saturday evening. It's 7:36 in the evening now. People are still around listening to you. And I'm sure if we let it go on, it would still continue for an hour. So thanks for your time. And we will take the chance to pick on you again one of these days and organize another session with your permission, please.
Thanks to IW Mumbai branch for the initiative and making all the arrangements and going into depth of this presentation. And I also have to thank our own team, WeldWell team, for massive job of emailing to hundreds of thousands of people in India and collecting 350 people is a big job. So thank you once again to all of you.
Thank you.
Thank you.
Thank you very much.
Thank you.
Bye, everybody.
Bye,
Thank
Sam.
you. Good evening to all.
Bye-bye.
Good evening.
Good evening, all participants. Thanks a lot for attending. And we'll have another interesting topic for you coming soon. Thanks for tuning
Thank you very
in.
much, everybody.
Bye-bye.
Thank you.
Thank you. Bye-bye.
Bye-bye.